I'm going to go over light water nuclear reactors. These are the reactors most commonly used in all the reactors in the United States. See the nuclear reactor core. Inside the core are the nuclear fuel rods, and those fuel rods produce heat, which then, in turn, is used to heat the water, which comes into the reactor and run the turbine. The coolant that goes around the reactor core, once it is heated up, turns the water into steam. The steam is used to turn the turbine. The turbine is connected to an electrical generator, and which in turn generates electricity. However, this is only 25% efficient. One reason for that is 75% of the energy is lost to heat. It's hard to control heat. The heat energy is lost to the environment. None of this harms the environment directly. There's no carbon dioxide emissions from this reaction. However, this warm water can be problematic. None of the reaction is exposed to the environment. The water from the environment is used to cool the reactor, but indirectly. The heat exchanger absorbs the heat from the coolant and then goes into the turbine, which runs a generator. The heat is removed from the water and returned to the environment. There might be some warm water in the environment, but no radioactive material is exposed to the environment. So the control rods are contained in the nuclear reactor core, and that core is surrounded by concrete and steel, and yet another layer of concrete to protect it from the environment in the event of a meltdown or the possibility of a meltdown. Now we'll talk about how these rods are controlled and how that energy is transferred. The coolant may need to be replaced at some point, and then storage of that coolant would be required. As well as fuel rods every 8 to 10 years, depending on how much is used. Try the quiz. Now, nuclear fission. Using uranium-235 is all set off by a single neutron. The neutron collides with an atom, and nuclear fission occurs. The nuclear fission separates uranium into krypton and barium, and as a product of that, 3 neutrons are produced. Those 3 neutrons then would go on to hit more uranium-235 atoms and continue the process all over again. This is called a nuclear chain reaction. The breakdown of one atom results in neutrons, which result in the breakdown of 3 more uranium-235 atoms. Again, the whole process is caused by a single neutron. All this energy results in tremendous amount of heat energy that is produced, and that heat is absorbed by the surrounding water. And then the water creates steam. But to control this reaction of the uranium-235, you need to control the neutrons, since that's what's causing the reactions. So we can do this by inserting what are called control rods. The control rods, to control the reaction, are inserted in between the uranium to absorb the neutrons that are produced through nuclear fission. You control the neutrons, you control the rate of the reaction. If you take the control rods out, then there's no reaction whatsoever. The good thing about nuclear fission is that you do not need a lot of uranium, and almost no greenhouse gases are produced. Because no carbon dioxide is produced, because you're not burning anything. It's relatively safe, and if something goes wrong, it goes terribly wrong. But for the most part, nuclear power plants, once they go online, there's very few problems throughout the course of the reactor. You've heard of a few, I'm sure, like 3 Mile Island and Chernobyl, and most recently the Fukushima plant in Japan as a result of the tsunami. Now let's look at some of the negative sides. One of the biggest is its low efficiency, which is almost zero. The amount of energy that you get from a nuclear reactor is only 25% to begin with. The 75% of the energy of that is lost to the environment. So really, you're getting 25% energy. But of course, there's more to it than that. It goes into the reactor. You have to mine the uranium or plutonium, and you have to transport it. So mining and then transporting, and eventually storage of the radioactive material has to occur. So you lose 75% to heat, about 9% to mining and enrichment and transportation of the material. And you lose another 8% just to store the stuff when you're done. You're talking about 92% loss. So that means at best you have 8% gain in energy. But then other scientists have mentioned you also have to incorporate the total cost. So you have to look at the cost of the environmental impact of building and taking down a plant after it is aged. Then you're actually going negative in terms of energy production. But at best you'd have 8% energy gain of the energy production. That's very inefficient compared to something like coal, for example. Another problem is the leftovers from the reactor. Once it's been technically spent, it is still highly radioactive. One study showed that if you had a sample of uranium that was 10 years old, sitting 3 feet away from it, it would kill you in 3 minutes. So it's still very radioactive. Enriched uranium that has not been depleted, 35 pounds of it or 15 pounds of plutonium is all that's needed to make a typical atomic weapon. You could do it with less than that, it just wouldn't be as effective. But any amount of spent uranium or plutonium could be used to make what's called a dirty bomb. All that does is basically disperse the radioactive material by taking the spent material and attaching it to something that explodes and blowing it up in an area and spreading those particles into the air. Of course, there are some trade-offs. For coal, a good thing is that it has a high net energy yield. You can produce a lot of energy, and it's very efficient for the coal that you do burn. Nuclear is the exact opposite. It's very inefficient. Like I said, 8% at best. The bad thing about coal is it produces a lot of carbon dioxide and sulfur, like we talked about before. And nuclear doesn't produce any carbon dioxide. While you're doing nuclear fission, you do produce, of course, some during mining as well as transportation. Coal, you have to get more of it, about 8 tons of coal per every tiny pellet of uranium that you would use. So you need more of it, a lot more coal. That's another positive side of uranium, is that you don't need a lot of it. A little goes a long ways. You don't have to disturb the earth as much as you would while you're mining for coal. As far as the cost, you're not looking at environmental cost. If you're not looking at environmental cost, the cost is relatively cheap for coal. That's why most countries use coal for their major source of energy. As for nuclear, exact opposite. The cost is extremely high, about $14 billion to build one nuclear power plant. So it's not economical to run. Tons of government subsidies go into running these plants. Nobody's going to say, hey, I'm going to start a nuclear reactor and make some money off of it, because the money is just not there. The cost is too much. Too much, especially these days with security. To have to watch the plant and take care of all the waste and protect it is extremely expensive. The enrichment of the refinement of uranium is also very, very expensive. So for your assignment, go to Moodle and post your opinion. What should we do about nuclear energy in the future?